So today we take a look at polar coordinates. Polar coordinates are kind of cool depending on what you had before you got to Calc 2. You may have seen some things with polar coordinates. You may not have any idea what polar coordinates are. So this section, we're going to take some time to go through it, is an introduction to polar coordinates. So if you've never seen them before, I'll sort of walk you through what polar coordinates are. If you know a little bit about this, come along for the ride. And then in the next section, we'll actually get to what we're going to use polar coordinates for and the calculus that's inside of polar coordinates. So a polar coordinate is another way of finding locations for things on a graph. Normally, if you were in what we call rectangular coordinates or Cartesian coordinates, you would define everything in terms of x and y. If you're in polar coordinates, then everything is going to be defined in two ways. You're going to start with some pole, right? This point over here will be the pole. In xy terms, you might think of it as the origin. And then you're going to have two pieces of information. You're going to have an angle and you're going to have a radius. So a polar coordinate will tell you first what angle that you should turn towards and then how far you should go, which means instead of things being determined in terms of x and y's, things are going to be determined in terms of r and theta. So for example, and there's a whole PowerPoint that I put together that goes with this too. If I wanted to look at the point 2 comma pi over 3, all right, then I would look at my axis, and I would first mark off roughly pi over 3, and then I would go across with a radius of 2. So maybe this is 1 unit away, this is 2 units away. So my point would be right here, and that would be the point 2 comma pi over 3. Now the funny thing about polar coordinates is there's more than one way to name every point, because suppose that instead of starting at the pole and going up here, pi over 3, I decided I wanted to walk in the other direction. I wanted to walk this way, backwards around my unit circle, until I got to pi over 3. So instead of going pi over 3, I would go negative 5 pi over 3. But if I look at this angle, this is considered going forward. So I would go forward 2 units in the direction angle-wise of negative 5 pi over 3. That's a second way to name that same point. Oh, but wait, there's more. Suppose instead of coming up here to pi over 3, I decided I was going to walk around to the other side here, which would be at 4 pi over 3. But 4 pi over 3 goes down this way. I want to go the other direction. So I'm going to walk myself around the unit circle until I get to 4 pi over 3, and then I'm going to walk backwards 2 units. Okay, so I can have such a thing as a negative radius. If 4 pi over 3 goes down, pi over 3 goes up. So I'm going to go up to that same point by going 2 units backwards. All right, what's another option? Another option is that I could start here and I could walk backwards 2 pi over 3. All right, so I could walk backwards 2 pi over 3, and then I could walk in the direction backwards for 2 units. So instead of going in this direction, 2 pi over 3 negative would be the same thing as 4 pi over 3 positive. I can go backwards 2 units and still end up at that same point. So you notice I've got 4 different colors of ink, and I got 4 different ways to name that same point. 2 pi over 3, 2 negative 5 pi over 3, negative 2 4 pi over 3, negative 2 negative 2 pi over 3. All 4 ways are ways to name that same point. And then I could take each of these and I could just add 2 pi to them. So instead of 2 comma pi over 3, why not 2 comma 7 pi over 3? All that means is I went around the unit circle more than once before I got to my point, right? So I came over here, I spun all the way around the unit circle, and then I went a little bit more until I got to pi over 3. So I still got to the same point 2 units away. It just took a little spiral before I got there. So there are now an infinite number of ways to name every point on the polar plane, whereas in rectangular coordinates, that is not the case. All right, so I've got this lovely PowerPoint put together. Let's take a look at an introduction to polar coordinates and polar curves. This will be broken up into a couple of videos. We'll get some of the polar coordinates done now, and then we'll look at polar curves as we go. So the polar plane defines things in terms of r's and thetas instead of x's and y's. I had already looked at this. The angle gives you the direction. The radius tells you how far to travel. I don't know if you've ever seen a piece of polar graph paper, but here's an example of a piece of polar graph paper. All right. This one is like a super duper polar graph paper because it actually goes down to 12ths. Oftentimes you don't see them broken down into 12ths. But you see, here's your 0. Here's your pi over 6, pi over 4, pi over 3. So if somebody said I want to find the point 3 comma pi over 6, right? Where is 3 comma pi over 6? Here's my line that defines pi over 6. And then all those circles are the radii from the center. So here's 1, 2, 3. Here's the point 3 comma pi over 6. But could I get there by going the other direction here, right? 7 pi over 6. Sure I can. If I went around the unit circle till I got to 7 pi over 6 and then walked backwards, right? So I can go to 7 pi over 6 and then I can walk backwards 3 units. That's another way to name that same point. Or I could start here at 0 and I could go around the unit circle this way, 11 pi over 6 in reverse, so I could go negative 11 pi over 6. And when I do that, the angle is going up to the right. So I would walk forward 3 units to get there. Okay, so a positive and a negative. And then the other option is that I decided to start at 0 and walk backwards until I got here, which is what? How many pi over 6s? 3, 4, 5 pi over 6, so negative 5 pi over 6. When I do that, forward would be considered in that direction, but that's not where the point is. The point is up here. So how do I get back there? Walk backwards 3 units. So you notice that the way that this works is that you've got positive, positive, you got negative, positive, positive, negative, and negative, negative. Those are the 4 choices for coming up with, that's a 6 in the bottom. Those are the 4 choices for coming up with an angle. Then, of course, for each of these, if I added a 2 pi to all of those angle measures, I could create additional names for those points where I basically spin around the unit circle more than once. Okay, so that's a piece of polar graph paper. It's a rather intricate piece of polar graph paper, but it works. All right, we talked about this one already. Actually, we use that same problem. Here's how you convert back and forth. How do you convert back and forth between polar and rectangular? Which of these 4 equations you use depends on what you have and what you want. So these first 2 are for going from polar to rectangular. In other words, you have a radius and an angle measure. You want to get out an x and a y. So this works for both converting individual coordinates and for converting entire equations in terms of x's and y's from things that are given in terms of r's and thetas. In this case, you're going from rectangular to polar. So you have x's and y's. The first equation uses the x's and the y's to get a radius. The second equation uses the x's and the y's to get an angle measure. You realize that if you have a radius of 1, then these are just the equations that define the unit circle, right? 1 times the cosine of theta, 1 times the sine of theta. So you might think of these first 2 equations as defining the r unit circle instead of just the unit circle where the radius is 1. What if you have a circle where the radius is bigger than 1, right? So you've got an r unit circle. That's how you do it. All right, so those 4 equations should stick in your head somewhere because you're going to see them as you go back and forth. All right, so let's take a look at a couple of examples. The first one I picked is a relatively easy one because I want you to see physically how they're related to each other. So convert that first one to rectangular coordinates. So the x-coordinate we said was r cosine theta. So the x-coordinate will be 2 times the cosine of pi. The y-coordinate will be r sine theta, so r times the sine of pi. Now the cosine of pi is negative 1, so I get 2 times negative 1, which is negative 2. The sine of pi is 0, so 2 times 0 is 0. The rectangular coordinate is negative 2, 0. Does that make sense on my graph? Well, pi, if that's 0, top is pi over 2. This thing over here is pi. Here's the funny thing. If you go 2 units in the direction of pi, you're right here at negative 2, 0. So remember that there's an angle involved here too. So if you're going 2 in the direction of pi, that's what, for all of your life, you've considered the negative direction. Because on the coordinate plane, it does go in the negative direction. All right, convert these things to rectangular coordinates. So how do I convert those to rectangular coordinates? Well, I need a radius, and I need an angle measure. So from here, I'll use those same two equations as last time to come up with the radius, with the x and the y. So if x is equal to r cosine theta, the r is the square root of 3, and then I need the cosine of pi over 6. Well, the cosine of pi over 6 is square root of 3 over 2, so I get the square root of 3 times the square root of 3 over 2, which is 3/2. So that's the x-coordinate. For the y, we're going to again use r sine theta. So in this case, I get the square root of 3 times the sine of pi over 6. All right, so that gives me the square root of 3 times 1/2, square root of 3 over 2. So I found an x-coordinate and I found a y-coordinate. The x-coordinate is 3/2. The y-coordinate is square root of 3 over 2. Now, I'm not 100% sure if that's actually the exact right answer, but at least it makes sense to me that square root of 3 pi over 6 is somewhere in the first quadrant, and that it should be below the halfway mark, right? Pi over 4 would be the halfway mark. So this point says that I'm going a little bit further to the right than I am up. So at least intuitive to me, it makes sense. All right, the last example is going to end up right over the top there. So I'm going to switch over to my whiteboard. I want to convert -1, 1 to polar coordinates. All right, so let's do -1, 1 to polar coordinates. This time I've got to use another set. I've got to use that second set of equations, where this time I have an x and a y. I want to find an r and a theta. So I know that x squared plus y squared equals r squared. Throw some numbers in. -1 squared plus 1 squared equals r squared. And look what we get. 1 plus 1 is 2. All right, so if 2 is equal to r squared, then the radius is the square root of 2. Now, for this second part, we're going to have to think ahead a little bit. We know that the equation is that the tan of theta equals y over x. So let's put in the numbers that we know. The y value is 1, the x value is -1. So we get the tan of theta is equal to -1. Now, it turns out there's two places where this is true, right? One of them is in the second quadrant at 3 pi over 4. The other is in the fourth quadrant at 7 pi over 4. Now, which one do we want? Well, where is our point? -1, 1 means go over 1, up 1. So our point is up here in the second quadrant. So that gives us a couple of options for what we want as our answer. We could say, go over to 3 pi over 4, and then go forward square root of 2 units. Or we could say, go to 7 pi over 4, and go backwards square root of 2 units. But it wouldn't make sense to say go to 7 pi over 4 and then go forward, or you'll end up with a point that's down in that quadrant over there. So sometimes you are going to have to look at these things and figure out physically where you are in the coordinate plane and then adjust accordingly. So yeah, I'll get two values for the tan of theta, right? Theta could be 3 pi over 4 or 7 pi over 4 based on the tangent function that I have. Which one of those do I want? Well, depends on where I want that point to be, and so you got to look ahead a little bit to figure it out. All right. How about equations? Is it possible for us to convert equations between one and the other? So sometimes it's much easier actually to work in polar coordinates. This says convert r equals 2 to a rectangular equation. Well, when I do that, I've got to use some function that's got an r in it and nothing else. Well, how about this one? How about x squared plus y squared equals r squared? Except I'll replace the r with the 2, and right away I'm done. So r equals 2 is actually a circle centered at the origin with a radius of 2. And so what that means is that if I were to graph this, I would pick a whole bunch of different angle measures with a radius of 2. So here is a radius of 2 and the theta value of 0. Here's a radius of 2 and a theta value of pi over 6, a radius of 2 and a theta value of pi over 3, radius of 2 and a theta value of pi over 2, and so forth. And then I can keep going and going and going. And by the time I get done, I'll have created this circle that's got a radius of 2 and is not at all dependent on the angle measures. All right, here's another one. convert theta equals pi over 3 to a rectangular coordinate equation. So this time, I'm going to need something that's got no dependence on the radius, right? The radius doesn't matter. It's just dependent on the angle measure. All right, what can I do for that? Which one haven't I used yet? How about tan of theta equals y over x? And this time we'll replace the theta with a pi over 3. All right, so I'll end up with the tan of pi over 3 equals y over x. Well, what is the tangent of pi over 3? How can I figure that thing out? Well, go back to your old unit circle. At pi over 3, what are the coordinates? It's got to be either a 1/2 or a square root of 3 over 2. Well, the pi over 3 is up here, so the y value is higher than the x value. So the y value then must be the square root of 3 over 2, and the x value must be a 1/2. And so now if you take sine and divide it by cosine, you'll end up with the tangent of the square root of tangent of pi over 3 being square root of 3. So if square root of 3 is y divided by x, multiply both sides by x, and I get y equals square root of 3 times x. So this is an oblique line. All right, so you would draw at theta equals pi over 3 all these points with a radius of 5, with a radius of 4, with a radius of 2, with a radius of 0, with a radius of -1, and so forth, until you come up with this over here. Okay, and kind of cool that the slope of that line is actually equal to the tangent of the angle that you're given. All right, how about converting r equals secant theta to rectangular form? Well, what formula should I use for that? I don't have any formulas with secants, so why don't I instead look at r equals 1 over the cosine of theta? All right, multiply both sides by cosine theta, and I end up with r cosine theta equals 1. Well, r cosine theta, didn't we say that x was equal to r cosine theta? So I end up with x equals 1. It's a vertical line. Okay, maybe that one doesn't jump out at you as intuitive, but it turns out it is. It works. All right, let's take a look at one or two other things here. Suppose I want to convert this guy to rectangular form, r equals 2 cosine theta. Well, I know what to do with x equals r cosine theta, but this is not x equals r cosine theta, this is r equals 2 cosine theta. Well, if I had an r cosine theta, I could probably do some wonderful things with it. So why don't I try to introduce it by multiplying both sides by r, right? And then maybe I'll end up with an r cosine theta, but on the right-hand side. So multiply both sides by r. So if I do that on the left side, I end up with an r squared. On the right side, I end up with a 2 times r cosine theta. This r cosine theta is actually x. But I can't now have an equation that's got x's and r's all mixed together, right? This thing over here is a 2x. On the other side, we know that x squared plus y squared equals r squared. So I end up with x squared plus y squared to replace that r squared. All right, what follows from here is just a little bit of completing the square to try to find out what it is. So let's move the x squared over to the other side. Move the 2x over to the other side. All right. And then I'm going to add a 1 to both sides because I know that works for completing the square, which means that this first piece then becomes x minus 1 squared plus y squared equals 1. And all of a sudden I figured out that it's a circle. It's got a radius of 1, and it's got a center of 1, 0. Because remember, it's x minus the x-coordinate squared, y minus the y-coordinate of the center squared. So if I change the sign here, I get a 1. So the center is at 1, 0. So its center is at 1, 0. It's got a radius of 1, so that means it touches the axis here, comes around like that. Okay, so that's what that is. R equals 2 cosine theta in rectangular form looks like this. So there again is an example of something that looks nicer in polar form than it looks in rectangular form. All right, I may have to swap to do the other. So y equals 3x plus 2 in polar form. Let's look at that on the other board. So I want to take y equals 3x plus 2 and put it in polar form. And then this will be the last example. Here we'll do another video with the graphs. Does this look nicer in polar form than it does in rectangular form? Yeah, let's see. Let's replace the y's with r sine thetas and the x's with r cosine thetas. Now my goal, if possible, is to solve for r. So I want r in terms of theta. Okay, how can I do that? Well, the first thing is if I'm going to have any chance of doing it, I got to get everything with an r on the same side. So let's do an r sine theta minus a 3r cosine theta equals 2. Now that the r's are on the same side, factor the r's out. So I get r times sine theta minus 3 cosine theta. And now divide both sides by sine of theta minus 3 cosine theta. And what you end up with is r equals 2 over sine theta minus 3 cosine theta. So not everything in polar form is easier than something in rectangular form. In this case, it would be easy for me to graph y equals 3x plus 2. It's just an oblique line. Y-intercept is 2. Slope is 3. But in polar form, is it possible to put things in polar form that's a line? Sure. Pick different values of theta, and you'll end up with that same line, just defined a little bit differently. The graphs that we can come up with for these things are really cool, and I'll show you them next.